We're asked to determine where the function h of x is continuous. Remember that most of our functions will be continuous on their domain. The main exception being a piecewise defined function, in which case it may or may not be continuous on the domain. We have to investigate that split point. But so for this one here, we have a rational function. I need to find out where I'm dividing by 0. So we're going to factor the denominator. For 6 OUs, 2 and 3, and my signs have to be different. And then just figure out where is that equal to 0. So we set each factor equal to 0 and solve. So that means then that x is equal to a positive 2 or x equals a negative 3. Remember, those are my bad numbers, so that's what x cannot equal. So really all real numbers except 2 and negative 3. Now the directions are going to specify to write it using interval notation. So we will go from negative infinity to negative 3, union the interval from negative 3 to 2, and then the open interval from 2 to positive infinity. And that'll be my final answer. So that is the domain of the function. It's also where it's continuous. Okay, for question number 2, we're asked to find the domain of the function. With radical functions, if it's an even root, a square root, or a fourth root, then we have to watch out for imaginary numbers. If it's an odd index, the cube root or the fifth root, then there's no issue. So since this is the square root, I need to make sure whatever is inside or underneath the radical is non-negative. So I have to have 4 minus x greater than or equal to 0. Otherwise, remember, like the square root of a negative 4 is 2i. We don't have imaginary numbers. We're only going to deal with real numbers in here. Okay. So come back up here solving this. I get add x both sides. So 4 has to be greater than or equal to x, or if you read it backwards, x is less than or equal to 4. So my domain is going to be all real numbers less than or equal to 4. So in interval notation, that's negative infinity up to 4. If I had asked you where this function was continuous, my answer would be the same. It's continuous on its domain, so from negative infinity to 4. We're asked to find the limit as x approaches 5 from the left or from below. So looking at my graph, as I get really close to 5, but from the left-hand side, so as x comes in this way close to 5, what is my graph doing? And so my y values are decreasing without bound. Therefore, we would say that the limit is equal to negative infinity. Let me go ahead and, so we've got this graph here, add a couple more limits to it. So let's look at the limit as x approaches 5 from the right-hand side, or from above. Okay, so what happens now is my x values approach 5 from above. If you trace the y values on your graph, you can see that they are increasing without bound. So my limit as x approaches 5 from the right will be positive infinity. And let's go ahead and see what happens. What's the limit as x approaches positive infinity? So now I'm letting my x values increase without bound. So as x moves out along the x-axis this way, x approaches infinity, my y values are approaching 0. They never equal 0, but they approach 0, so my limit is equal to 0. We're asked to find the limit as t approaches infinity. Okay, so there's basically 2 ways we could do this. If you're comfortable with horizontal asymptotes, then you could find the horizontal asymptote, which is, by definition, the limit as t approaches positive or negative infinity. And then the other option is to use a table. So most of my students would use a table just because we're comfortable with tables. We know how to do a table. So I'm going to do that one first. So we're setting up our values for t and v. And again, t is approaching infinity. So don't use things like 7, 8, and 9. You want to get really big numbers. So I'm going to go with 10, 100, and then 1,000. Okay, so plugging these into my my formula over here. So I'm going to have, like plugging in a 10 for my t. And then over here, I end up with 10. I get 25.8. All right, same thing. I'm going to plug in 100 everywhere. And I got 21.62. And then plugging in 1,000, I get 21.06, and a lot more digits. So it seems pretty obvious to me that the values for v are approaching 21. So my limit is going to be 21. Okay. When you're doing a table for me, make sure you throw at least 3 values. And like I said, if you're getting, if you're approaching positive infinity, make sure your numbers are getting really big. Okay, another option we said was to go ahead and find the horizontal asymptote. And there's a couple different ways of doing this as well. I'm not real picky as long as it's, good math. So looking at my function, v of t equals 37 minus 16 t squared all over t plus 2 squared. So looking at this fraction piece of it right here, I said, all right, so the degree of the numerator and the denominator are the same. If I were to FOIL out the denominator, we'd get t squared plus 4t plus 4. So I've got a t squared in the top, t squared in the bottom. That means for this fraction piece, as t approaches infinity, the horizontal asymptote will be 16 over 1, or just 16. But, we've got to put it together with the other piece. So we have 37 minus my 16, and so the limit will be 21. All right, so like I said, same answer, slightly different approach, and I really have no personal preference for which way you do it, as long as you show me some work. All right, for question number 5, we're asked to find the limit. This one's a lot nicer because we can just plug and chug. That really should be your first approach. You can't do that with infinity, obviously, but substituting the value, if you get a real number, then that's your limit. So let's see, I would take the square root of 3 squared plus 7. 3 squared is 9, so 9 plus 7, the square root of that. Square root of 16 is 4. 4 is a real number. That's my answer right there. We're done. So for number 6, we're asked to find dy dx. So I'm asked to take the derivative. A lot of times when you're taking derivatives, you want to rewrite them first algebraically so they can fit into our rules. So one issue I have here is this x to the third in the denominator. You don't want to use the quotient rule for this. Just since it's a single variable, we can just bring it up. So my first step is to go ahead and, like I said, use algebra to simplify. So y is equal to 1/3 x to the negative 3. And then for the second fraction, you can leave it as it is, or if you prefer, write it as 1/10 x to the 7th. But now we can go ahead and use our basic power rule. So remember, if you want to take the derivative of x to the n, you bring down your exponent, decrease it by 1. Okay, so y prime or dy dx is equal to, I have 1/3 times, bring down my exponent, negative 3, decrease it by 1, so my new exponent's a negative 4. And then for the second fraction, same thing, I've got 1/10 times, bring down my exponent, so this becomes 7x to the 6th. And now we've got to clean this up a little bit. So multiplying here, 1/3 and a negative 3 gives me a negative, and then x to the negative 4th. And then the second fraction is 7 over 10 x to the 6th. And so now that negative exponent, again, I can rewrite it as negative 1 over x to the 4th power. And then plus 7/10 x to the 6th, or you may see it as 7x to the 6th over 10. Again, I'm not going to be real picky about that. If it's a multiple choice, make sure that you can match their answer. All right, so now we have another derivative. Same thing, I've got stuff raised to a power. If it's in the denominator, then you have to ask yourself, do I need to use the quotient rule or not? This time I don't have to use the quotient rule because the numerator is just a constant. It's a 4. If I had a 4w, then I would have to go ahead and use my quotient rule. So no quotient rule this time. Again, rewriting it using algebra, then this is going to be equal to 4 times w squared plus 3 to the negative 5th power. And now I want to take the derivative of this expression with respect to the variable w. Okay, so notice I've got stuff raised to a power. So I need to use my general power rule. And the general power rule, that's one of our chain rules. So if I've got some function of x raised to the power, and I want to take the derivative, I'm going to bring down the exponent, decrease it by 1, but I also have to multiply it by u prime, the derivative of u. Okay, so for this example here, I've got 4. I bring down my exponent, I decrease it by 1, So w squared plus 3 to the negative 6 power. And now I multiply it by the derivative of what's inside. So I've got to multiply the derivative of w squared plus 3. And I get 2w. Okay. So now I have to clean this up. The coefficients I can multiply together. So the 4, the negative 5, and the 2w can all be multiplied or combined. So I get negative 40w. And then this quantity in parentheses is going to be on its own. I'd be happy with your answer left like this. If you need to match it with a multiple choice answer, you may need to write it a little bit more. So negative quantity, we're going to bring it down below. So I have a negative 40w all over w squared plus 3 to the positive 6 power. And that's my answer simplified.